For years, training machine learning intraatomic potentials has followed a predictable pattern. You pick an equivariant architecture, you pull from a quantum chemistry dataset, and you hand it off to Adam or AdamW. It works. It's reliable. But it's also largely unoptimized. While the community has poured massive effort into better architectures and larger datasets, the training dynamics themselves have been treated as a fixed component. That's exactly what this research challenges. By systematically benchmarking matrix-structured optimizers from the large language model literature, specifically Muon, SOAP, and their hybrid SOAP-Muon, we found that optimizer choice is not just a hyperparameter tweak. It's a first-class design axis that dramatically impacts convergence speed, final accuracy, and label efficiency. To understand why this matters, we need to look at how MLIPs are actually trained. These models approximate the potential energy surface of an atomistic system by fitting a neural network to quantum mechanical reference data. The network maps atomic positions and species to a total energy, which decomposes into local atomic contributions to ensure size extensivity. Forces are then obtained automatically by taking the negative gradient of that predicted energy. Training minimizes a weighted combination of energy and force, mean absolute errors. The loss landscape here is notoriously anisotropic. Some directions in parameter space change the loss rapidly, while others are flat. Vanilla gradient descent struggles here, which is why we rely on preconditioning. Preconditioning rescales the gradient to account for the local curvature, allowing larger steps in flat directions and smaller steps in steep ones. Adam approximates this curvature with a diagonal matrix, tracking a running estimate of the element-wise squared gradient. It's fast, memory-efficient, and widely used, but it completely ignores the geometric structure of the weight matrices themselves. When you have a linear layer with a weight matrix, Adam treats every parameter independently. That's a massive simplification. Matrix-structured optimizers like Shampoo, Muon, SOAP, and SOAP-Muon were developed to address exactly this. They exploit the full covariance structure of the gradients, which is why they've driven such dramatic speedups in training large language models. Let's break down how these optimizers actually work under the hood. Shampoo builds left and right preconditioners using the accumulated uncentered row and column covariances of the gradient matrix. It essentially tracks how gradients correlate across rows and columns. Muon takes a different route. It applies a Nesterov-style momentum update, then projects that momentum matrix onto the nearest semi-orthogonal matrix using efficient Newton-Schulze iterations. This orthogonalization step effectively normalizes the update direction along dominant spectral modes, preventing overshooting while preserving geometric information. SOAP combines the best of both worlds. It observes that Shampoo is mathematically equivalent to running a DAF-vector in the eigenspace of the preconditioner. SOAP replaces that step with an AdamW update in the eigenbosses, then projects back to the original parameter space. SOAP-Muon extends this by adding the Muon-inspired orthogonalization step after the standard SOAP update. The result is a hybrid that leverages adaptive preconditioning while maintaining stable, geometrically aware updates. We implemented these optimizers directly into the NequIP framework and benchmarked them across two physically distinct systems. First, liquid water modeled with NequIP, an equivariant graph neural network that propagates features via message passing. Second, the solid acid electrolyte cesium dihydrogen phosphate, or CDP, modeled with Allegro, which builds many-body representations through iterated tensor products within a strict local cutoff. Both architectures are E3 equivariant, meaning their internal features transform predictably under rotations, reflections, and translations. This symmetry is crucial for data efficiency and physical consistency. Under full energy and force supervision, the results are clear. SOAP and SOAP-Muon consistently outperform AdamW in both convergence speed and final accuracy. On CDP, SOAP reduces energy mean absolute error by 9%, while SOAP-Muon cuts force error by 14%. On water, SOAP-Muon reduces energy error by 24%, and SOAP reduces force error by 19%. Muon alone shows mixed results. It improves on CDP, but actually underperforms AdamW on water, particularly for energy prediction. This discrepancy is worth noting, as it suggests the orthogonalization step can introduce instability in certain loss landscapes, especially when not carefully tuned. But the real story emerges when we look at reduced force supervision. Computing force labels via density functional theory is relatively cheap due to the Hellman-Feynman theorem. But for higher levels of theory like coupled cluster methods or diffusion Monte Carlo, force evaluation is prohibitively expensive. Even when forces are available, many training pipelines deliberately use only a subset to save memory and compute. We tested how these optimizers perform when force labels are systematically removed, down to energy-only training. Here, the advantage of matrix-structured optimizers becomes dramatic. On CDP, SOAP-Muon trained with only 50% of the force labels achieves accuracy comparable to AdamW trained with 100%. SOAP shows a nearly identical pattern. Both methods remain clearly superior to AdamW, even at 10 and 5% force supervision. On water, the trend is slightly less regular, but SOAP remains the most consistently competitive method across all sparsity levels. This tells us that improved optimization can partially compensate for reduced access to force labels, lowering the amount of expensive quantum mechanical data needed to reach a given accuracy threshold. Speed is equally important. We measured wall clock time to reach AdamW's minimum validation force error. On CDP, SOAP reaches that target 4.9 times faster. On water, it's 5.8 times faster. These gains are remarkable because matrix-structured methods actually incur higher computational cost per optimization step due to the preconditioner updates. The wall clock advantage means they reduce the total number of epochs needed by an even larger margin. The improved conditioning more than compensates for the per-step overhead. Accuracy and speed mean little if the resulting potential energy surface doesn't reflect reality. We validated the trained models by running molecular dynamic simulations and comparing structural and dynamical observables against ob initio reference data and experimental measurements. For CDP, all fully force-supervised models faithfully reproduce ob initio molecular dynamics, matching radial distribution functions and mean square displacement behaviors. The differences become stark in the sparse label regime. At 5% force supervision, the SOAP-Muon model remains stable and accurately reproduces the proton diffusion activation energy, landing at 0.42 electron volts. That sits squarely within the experimental range of 0.39 to 0.43 electron volts. Under the exact same conditions, the AdamW model becomes catastrophically unstable, with trajectories diverging almost immediately and producing non-physical results. For water, both AdamW and SOAP maintained physical fidelity across all sparsity percentages tested, though SOAP still converged faster and reached lower error baselines. There are practical implementation details worth highlighting for anyone looking to reproduce this. Equivariant frameworks like ENN store the weights of their tensor product operators as flattened one-dimensional parameter vectors, even though those weights act as structured matrices during the forward pass. Adam-style element-wise optimizers can operate directly on these flattened vectors. But matrix-structured optimizers are shape-sensitive. You have to unstack the flattened parameters, restore them to their instruction-wise matrix or tensor blocks, apply the structured update, and then flatten them back. We partitioned parameters into groups. Intermediate linear weight matrices went to Muon or SOAP-Muon, while type embeddings and readout layers stayed on Adam. This split is critical for stability. We also found that SOAP-Muon requires smaller learning rates, often an order of magnitude lower than the other optimizers, and its hyperparameters, particularly the singular value power and momentum coefficients, show dataset-dependent sensitivity. For practitioners who want a single default optimizer that requires minimal tuning, SOAP is the clear recommendation. The landscape of machine learning intraatomic potentials is shifting rapidly. As we move toward universal foundation potentials, label efficiency and convergence speed will become increasingly important. Training techniques, exemplified by optimizer choice, can no longer be an afterthought. Matrix-structured optimizers like SOAP and SOAP-Muon offer a direct path to faster convergence, higher accuracy, and robust performance under sparse supervision, without sacrificing physical fidelity. The optimizer is not just a training detail. It's a fundamental lever for scaling scientific machine learning. If you're training equivariant potentials today, it's time to look beyond Adam.